So let's go ahead and look at, we did example number 1 on page 388. We did the sleep p-value by entering in the data points in your L1, using that to do the t-test. Okay, we're good with that. We actually did example number 2 also by kind of explaining how the critical value method would work in this. So in other words, if we did not use the technology, right? We explained how we could do that. And then example number 3, okay, so we did example number 2. Let's kind of briefly look at example number 3. Example number 3, it says we're doing the same thing. Now we're going to do the critical value method. Really, critical value method is kind of like the p-value method, but slightly different. Okay, so in that one, we're actually going to find the critical value. Okay, we're going to find the critical value. So, where are we at? We are in example number 3. If you see there, if you look there, if we find the critical value, which we could find by using what? How can we find the critical value? What was our critical value? Remember, our critical value for the t was what?
U, x bar minus u.
T is going to be equal to this guy minus this guy over S over square root of n, right? And we found this, and we can find this, right? So that's what they did. They found that. They found that to be negative 1.796, 1.796, and we would go like this, and we would find this value here, right, at this value right here. And if you do that, if you look at that, where are we at? Okay. So this is the critical value for it to pass our test. So it can pass a test, or we can reject the whole at that point, right? But what did we actually found? We found that the value was actually going to be negative 0.290, right? So this value is not in the critical value, so you cannot reject the whole, right? Okay. So it's the same thing. Instead of looking at the p-value versus the alpha value, you're going to say, well, this is the corresponding alpha. This is the one that we actually found. So let's compare these two. Okay, it's kind of the same thing. So just realize that's there. And then go to example number 4. If you look at example number 4, there was something called the confidence interval method. Disregard that. Don't even read that. It's going to confuse you for anything, if anything else. Okay? So just forget about that. Blah, blah, blah. Shall we do example number 5 together? Let's go ahead and do example number 5. The data set 3, body temperatures in appendix B, includes a measured body temperature with blah, blah, blah. When we do that, we get a mu n is equal to 106, mu is x bar is equal to 98.2, with a standard deviation of 0.62. Okay? Use, so let's go ahead and see if we can do the alpha is equal to 0.05 significant with a significance level test to 98.6. So what are we testing here? What's our hoe in our heart? This is the most important thing, right? What are we actually testing? We have 98.6. The hoe is going to be at 98.6, correct? The hoe is going to be, the body temperature is equal to 98.6. What is the ha going to be? Is it going to be doesn't equal to, or is it going to be less than? What are we testing? Let's make sure we understand what we're testing here. To test the common belief that is 98.6. So actually we're testing that it's not equal to, correct? So ha would be equal to, ha is, mu is equal to, not equal to 96. Okay, so we get this sign. This means what? Automatically when this comes up, in your head you're thinking two-tail, right? It's a two-tail, right? Alpha is going to be equal to 0.05. Okay? So how am I going to do this? So what do I need to do? I'm going to use the t-test method, right? So let's go ahead and bring your calculators out. We'll do t-test. T-test with, we know n is going to be equal to 106. X bar is going to be equal to, you gave us these values, right? 98.2. And S was equal to? Point what?
62.
62. Okay. So see if you can plug the numbers in and let the calculator chug and find out what. So what are we trying to find? We are going to find, when we do the t-test, it's going to tell us what important value. The p-value, right? Because we want the p-value, because we want to compare that with the alpha, right? Did anybody get the p-value by doing this?
Yeah, no, I just saw
You just
No,
thought
I
e
just-
to the negative, blah,
I
blah,
was
blah,
like,
blah.
I was like, oh yeah, me too. No, it's actually there. Don't worry.
Okay, so if you did this correctly, evidently the p-value is going to be equal to 1.4 what? 86?
4.036.
Times 10 to the negative 14th or something like that or whatever. It's like 0.00000000001, right? So it's really, really, really small. So in other words, yes, the p-value is smaller than the alpha, therefore we reject the whole. We have significant evidence that the mu is not equal to 98.6. In other words, paraphrasing, the 98.2 that we found here is so far away from this, it could have never happened by chance. It could have never happened by just getting a chance bad data set. Okay? All right? That's what we're thinking here, right? Okay? So we're good there. So that's how you do it. Okay. Alternative methods used when the population is not normal and is less than 30. What do we have to do when n is less than 30? What do we have to do? We have to do a dot plot or a histogram to make sure there are no outliers and no severe skewedness. Okay? So that's good. Let's go to part 2. This happens every once in a blue moon. Every once in a blue moon when you're doing a mean, they're going to actually tell you that the sigma is known. Okay, like I told you, most of the time this doesn't happen. There are 2 ways this happens. The rarest of all rarest is you actually do know the sigma of the population, okay? Which is very, very, very rare. The other thing that happens is that we're doing a study and there's a similar study that was done like years ago, and guess what? I'm just going to use or borrow and beg and steal the sigma from what they found there and call it good. And we're going to say the sigma is known. Okay? So what's the advantage if sigma is known? What can I do? What's the difference? Yeah, now I don't have to do the t-test. Because I know I have a known sigma. Right? If I have a known sigma, flip the page. Instead of S here that we had, instead of x bar minus mu s over square root of n, I get to now not use this. I'm going to actually use the sigma. Okay? And since the sigma is known, I do not need to use the t-test anymore. I can just use a z-test. Right? I can just say, okay, what's normal? We're just going to go not the t, but we're going to bring it up and we're going to call it a normal distribution. Just go from there. Okay? And you can see there on page 394, the test statistics now becomes a Z number, right, instead of a T. You do not have to worry about degree of freedom, anything like that. Okay? So just realize that does happen every once in a while. But again, most of the time it happens because you're borrowing somebody else's. And you're just going to say, whoa, magically wave the wand and say, this is good enough, we're going to use it. Okay? Okay, and that's it. We are done with 8.3. We are completely done with 8.3.